In this video, we'll be taking a closer look at radical reactions. With radical reactions, we're talking about the movement of single electrons. And so we represent this using a single barbed arrow. So we just have the one barb, not the two barbs, because only one electron is moving. So radical reactions involve homolytic or symmetric bond breaking. Symmetric bond breaking doesn't mean that we have to have the same atoms on either end of the bond. It just means that out of these two electrons, one of them goes to one atom and the other one goes to the other atom. So the two electrons are moving to each atom rather than both electrons moving to one atom. So out of this pair of electrons, we could have one of them move on to A and one of them moves on to B, giving us A with a radical and B with a radical. So the radical then is an unpaired electron. What used to be the shared pair, one electron goes to each atom so that now each atom has an extra electron. We can also have symmetric bond forming. Once again, it doesn't mean that our different atoms have to be the same. It just means that we get one electron from each atom. So we can point to the place where the bond is going to be, right? So we point in between because we're going to have a new bond between Y and Z, giving us something like this. So what was a shared pair becomes individual electrons. What was the individual unpaired electrons becomes a shared pair. So let's continue to think about radical reactions, but let's focus on the radical itself. So what is a radical? This is an atom or a group with a single unpaired electron. So a radical is an atom or a group with a single unpaired electron. Often it might be something that has 7 electrons when it wants 8, right? So it needs 1 electron to get an octet. So how can a radical obtain an octet? One way is to abstract an atom with its bonding electron. So here's our free radical, and it can form a new bond with A, so that A has to bring 1 electron with it, and then the other electron goes on to B. So this gives us a new bond between whatever our original radical was and A, and we form a new radical on B. So here we have a substitution and we formed a new radical. Another way that a radical can get an extra electron is by abstracting electrons from a pi bond. So this radical can take one of the electrons from the pi bond, but these electrons still remain associated with the carbons. So for example, one of these electrons can stay on this carbon, the other one can come over here and combine with the radical. Now what that gives, the radical is connected to the carbon on the left, which is still connected to WX. The carbon on the right is still connected to Y and Z, but the carbon on the right is now a radical. So overall, this is an addition, and we have formed a new radical. In the first example, this new bond comes from the radical and one of the electrons that used to be shared between AB. The new unpaired electron is what used to be part of the shared pair. In example 2, the new bond is made up of 1 electron that used to be the unpaired electron on the radical and 1 electron that used to be in the pi bond, and the new radical comes from one of the electrons that used to be in the pi bond. Let's look at an example of a radical reaction. And here we're looking at a radical halogenation. This is the chlorination of methane. So here's the overall reaction. We have methane can react with molecular chlorine in the presence of light and heat to form chloromethane and HCl. So overall, this is a substitution where 1 hydrogen is replaced by a chlorine. Now, for the mechanism of the reaction, here we're looking at the details of how do the bonds change, what's the order of the bond breakage and the bond forming. Notice we're starting without radicals and we're ending without radicals. So the radical has to be generated within the reaction, and that is the role of light and heat. So this is an initiation step where a molecule of chlorine will undergo homolytic bond cleavage in the presence of light and heat. So one of these electrons will move onto this chlorine, and one of these electrons will move onto the other chlorine, which gives us two chlorine radicals. This is called an initiation step because we go from 0 to 2 radicals. Now, this is actually a very inefficient reaction. So only a very, very small number of molecules are actually going to undergo this homolytic bond cleavage. So we have made some radicals, but we still have lots and lots of molecular chlorine around. Now, in the second step, we have a chlorine radical, and this can abstract an atom. So if chlorine grabs off a hydrogen with one electron, then that leaves the other electron on the carbon. So we have our hydrogen connected to the carbon. It's still connected to these two other hydrogens. And now there is an unpaired electron on the carbon. And then we also have the hydrogen with one electron has combined with the other electron and chlorine. This is called a propagation step because we start with one radical and we end with one radical. So we have a new bond between H and Cl, one electron from H, one electron from Cl, and then we have a new radical where this electron used to be part of the shared pair. Next, we have another step where this methyl radical can bump into a molecule of chlorine and the radical can abstract another atom. So this electron can come together with one of these electrons, and then this electron moves on to the chlorine. So this carbon is still connected to these three hydrogens, but now it is connected to a chlorine, and we have another chlorine radical. So this new bond is made up of one electron from the radical and one electron that used to be shared between the chlorine and chlorine. And then this unpaired electron is one of the electrons that used to be shared between the two chlorines. This is another propagation step because we started with one radical and we ended with one radical. Now, I mentioned that this step is very inefficient, and so there's only a really, really small number of chlorine radicals, lots and lots of chlorine molecules. So once this radical forms, it's much more likely to bump into a molecule of chlorine rather than bumping into a chlorine radical. So what we have here, after initiation occurs, these propagation steps are going to happen over and over and over again. So this is a chain reaction. Now, eventually, there will be some termination steps. And in a termination step, we go from 2 to 0 radicals. So we could have a chlorine radical bump into a chlorine radical, which will give us back molecular chlorine. We could have a methyl radical bump into a chlorine radical, and that will give us some chloromethane. Or we could have a methyl radical bump into another methyl radical, and that would give us a little bit of ethane. The radical halogenation reactions are interesting because it is a chain reaction. So we're going to learn more details about the radical halogenation, the mechanism, the limitations, all of this stuff. We'll learn about that later. For now, I just want you to focus on the idea of the radical reaction and the movement of single electrons. Notice in the first step, in the initiation step, we are going from no radicals to two radicals. we are breaking this bond. And when the bond breaking occurs, the electrons are moving away from each other. In the second step, we have bond forming and bond breaking. With the bond breaking, again, this pair of electrons, they're moving away from each other. One goes toward the chlorine, one remains associated with the hydrogen. With the bond forming, the pair of electrons are coming together from two different atoms. One electron comes from the chlorine, one comes from the hydrogen to form the new bond. So every time we have bond breaking, the electrons are moving in opposite directions. Every time we have bond forming, the electrons are coming together from opposite directions. So focusing more on the curved arrows, when it comes to radical reactions, then we have bond breaking might look like this, where out of the shared pair, one of them goes on to A, one of them goes on to B. And that will give us A radical and B radical. Another possibility is that a pi bond could break, and this pi bond, one electron would end up on the carbon and the other electron ends up on the other carbon. So our sigma bond is intact, but our pi bond is broken, for example. So in both these cases, the arrows are moving away from each other. The arrow starts at the bond and points to the atom where it ends up. Starts at the bond, points to the atom where it ends up. Here, the arrow starts at the bond, points to the atom where it ends up, and the same thing over here. The arrows are moving away from each other whenever we have bond breaking in a radical reaction. Whenever we have bond forming in a radical reaction, now the electrons are moving towards each other from opposite directions, giving us a new bond. Now, when both are happening at the same time, we have one electron coming together with another electron. And then from this bond, one electron's going this way and the other electron is going on to the B, giving us a new bond between the radical and the A, and then B is our new radical. Over here, we could have something like this. The radical and one of the pi electrons are coming together to form a new bond, giving us a new bond between the radical and the carbon, which originally held the electron. And then focusing on the bond breaking, one of these electrons was already used up over here. The other electron moves on to the second carbon. So this is still connected to Y and Z, but now it is a new radical. So just as we did above, here we have the bond breaking, the electrons are moving away from each other. With the bond forming, the arrows are moving toward each other because the electrons are moving toward each other, and we point to the space where the bond is going to be. Over here, with the bond breaking, our electrons are moving away from each other, so our arrows point away from each other. With our bond forming, our arrows point to the space where the new bond is going to be because our electrons are coming from different atoms to form a new shared bond. This takes care of our introduction to radical reactions. This is something that we will come back to later this year.